In this video, I will discuss solving a 2x2 system with matrices. Now, I want to help you build some intuition for doing this by hand. I've discussed there are many different uses of technology that you could apply to these ideas. This video is to talk about how to do a 2x2 system without a calculator though. So to set up, what we want to do right now is for some 2x2 matrix, I want to find another 2x2 matrix such that when you multiply that pair, the product gives us the identity. Now this matrix, where I have 1 in the main diagonal, is called the identity matrix for a 2x2 square matrix. And it's called the identity because when you take it times any other matrix, you get the original matrix itself. So what I mean by that is you're familiar with multiplicative identity with real numbers. If you take 5 times 1, you get 5 again. That works on both sides. 1 times 5 is also 5. So 1 is the multiplicative identity. This matrix works like 1 in real number multiplication. What we will do right now then is try to solve for x1, x2, x3, x4 such that this product would give us the identity. In matrix equations, we often use uppercase letters to denote matrices. So here this matrix is called our coefficient matrix, and I'm going to call that A. The inverse, I'm using inverse notation here for the 2x2 which we're trying to solve for. When we multiply those, they essentially cancel themselves out and I get the identity matrix. We often use an I to denote the identity matrix if you see that in any of our work. We want to find the equation for an inverse for any 2x2 to figure out when you can multiply and cancel out to get the identity. So using this information, in the last slide I set up a matrix equation. This matrix equation can be written and expressed as a system, or two systems, of linear equations. So if I multiply out on the left side using row by column, so matrix multiplication, we'll use 2 times x1 plus the next element in that row, 1, times the next element in the column, x3, and that equals 1, which was in the first row and first column I used to get the equation. So this equation comes from that first row and first column in the matrix equation. Like so, you can actually go ahead and use the second row times the first column and get a second equation. Notice I've stacked these together because I have two equations with the same two unknowns, x1 and x3. So these two equations, these will actually allow me to solve for x1 and x3. Similarly, using the second column, I get another two equations, and I have two equations with the same two unknowns. Now, if you already feel comfortable using other methods to solve systems of linear equations, you can go ahead and do so. Substitution, elimination by addition. You could even use graphing. Here, x2 and x4 are different variables. If you wanted to graph them, you could denote one axis to be for representing x2 values and the other for x4. I'm going to use substitution. Substitution happens to be one of our easiest methods. So given the 2x2 system on the left, I'm going to solve for x3. So using the first equation, I have solved for x3, and it gives me this setup 1 minus 2x1. By substituting that into the second equation, I now have a single equation with a single unknown x1, and I am able to solve for x1. If that was too quick, please take advantage of this being a video and pause and try to work that out yourself. Now that I have x1, I can substitute that in to this expression where I isolated x3. Substituting that in allows me to solve for x3, and I get another fraction, -3/5. I have now solved this 2x2 system, and I know what I need for values for x1 and x3. The other 2x2 system, I will similarly solve for the missing variables. So go ahead and take a moment and try that yourself. And when you've given that some time, go ahead and restart the video. I have x4 from the first equation. I solved for x4. Of course, you could have done this many different ways. You could have solved the second equation for x2 instead, or the first equation for x2, substituted that into the second equation. So you can have some freedom about that, but my work is indicated here, and you can kind of look at that. We both should have that x2 is equal to negative 1/5. By substituting that back in, I'll have x4 is equal to 2/5. I have now solved for all 4 of the variables that I was looking for. So now we have found this x1 through x4. We'll go ahead and substitute those in, and what you have found with me is that the inverse of the given 2x2 matrix is expressed here. So 4/5, negative 1/5, negative 3/5, and 2/5. I noticed some patterns among the old matrix, so I kind of want you to think about that. And maybe sometimes you might, when you work math problems, you don't feel confident. So I encourage you, check your work. Remember that we set this up trying to find a matrix such that when you multiplied these, you would get the identity. So we could always just check our work. Here I have A. This is the A inverse we just have. If you go ahead and take a moment and use matrix multiplication appropriately, so row by column, when I take the first row, so I'm taking the dot product of the vector in the first row of the first matrix times the column in the first column in the second matrix. When you find that product, you will get 5/5. Similarly, when you take the first row times the second column, you will get 0/5. 0/5 and 5/5 again. This gives us the identity 1, 0, 0, 1. And also, if you do this if you look at the product of A inverse times A, it actually works from both sides, which might surprise you because matrix multiplication is not commutative, but these inverses of each other, because they're inverses of each other, their product will cancel no matter which side you multiply from. So something to keep in mind. Now, looking at some patterns, because all of those were fractions, the entries all had a denominator of 5, I've factored that 1/5 out, and this is a scalar multiple, so all of those had a 1/5. I factored out the scalar multiple. So for scalar multiplication, this is kind of like factoring. I've pulled that 1/5 out. I've left the numerators inside representing those entries, so 4, negative 1, negative 3, 2. And you'll notice I want you to relate A inverse to the original matrix. You have some similar numbers. 4 and 2 are still here, but they're in different locations. Negative 1 and negative 3 have now taken the spots of 1 and positive 3. And so I noticed some similarities. What I want you to start thinking about is, we found the inverse for a particular 2x2, but how would I generalize this for any 2x2? And I encourage you, it's quite a fun exercise to go ahead and try this and see if you can actually determine where the equation comes from. What you would do is you would start from what we began with the x1 through x4, but you could put maybe dummy variables here, A, B, C, D. And if you work all of these steps through again, I know that you'll have a lot of constants and more letters than numbers. Some students are not comfortable with that. But if you'll work through that, you'll actually get an equation so that we could use this equation on any 2x2. If you had taken the time to work that out, you would find this equation for A inverse. This would have been our 1/5 earlier, this fraction out front, 1 over AD minus BC. You'll notice that's the product of the main diagonal times the opposite diagonal, BC. And for the 2x2, we swap the terms in the main diagonal, A and D, and I negate the terms in the opposite diagonal, negative B and negative C. And if you'll look back, this actually works for our previous example. Not only that, it's going to work for any 2x2 where this does give us real values. So pause the video and think about, is this always going to work for every 2x2? And if I gave you time to think about that, I think that you would tell me, well, since we can't have 0 in the denominator, a 2 by 2 may not always have an inverse, and that's completely correct. This term that appears in the denominator, AD minus BC, again, we talk about the bow tie, AD minus BC, the main diagonal minus so the product of the terms in the main diagonal minus the opposite values. So AD minus BC, that cannot be 0. A 2 by 2 will not always have an inverse. Its inverse does not exist if this term is equal to 0. That's so important, we actually give that a name and we call it the determinant. So for any 2 by 2, sometimes we'll put straight lines, it looks somewhat like an absolute value there, or we might call it DET of A, and that's just a short name for determinant. And if this value does not exist, then the inverse of a 2 by 2 will not exist. And I want you to take that and think about it in problems that I give you. If you could not solve an equation, there are a couple reasons why the determinant wouldn't exist. You could have the same line twice, or you could have a inconsistent system and you don't have enough information to isolate a single variable. So those are two reasons why you wouldn't be able to perhaps solve a 2 by 2 linear system. And your calculator will simply give you a determinant error, but you might need to consider what type of error you have. So for solving systems of linear equations with matrices, suppose that I wanted to solve this matrix equation. You'll notice I've used the same matrix from before. I've simply modified this a bit. I'm taking 2x plus 1y is equal to 1, 3x plus 4y is equal to 3. Perhaps this came from a word problem that I had started with, and this was the matrix equation. Well, I can isolate xy and solve for xy by finding A inverse, and for multiplication it is not commutative, and so matrix multiplication is not commutative. You do need to make sure you're doing it on the same side. Because I need to get x by itself, I want to cancel this A out front, so I'm multiplying by the inverse on the left, on both sides, and that's very important. It will cancel the A on the left when I multiply the inverse, and on the right side I will have A inverse times B. So really what happens is I get I times x here, but since I, the identity, it's like writing 1 times x, you don't always have to write the 1. I've left that out for this. X will be equal to the inverse times B. Fortunately, we already found the inverse of our matrix earlier, and so I've substituted that here. 1/5 times this 2 by 2, and B is simply 1/3. If you multiply these two matrices, and I do have a scalar out front, remember the scalar is just distributed to every term inside. So go ahead and take a moment, multiply this row, columns, or multiply those vectors. You should get 1/3 from this product, and since everything is times 1/5, I've gone ahead and put the 1/5 on the inside. So 1/5, 3/5. What this is saying is x, the first entry in that column, is 1/5, and y is 3/5. And of course you could check my work by substituting those into the original linear equations to see if you got it correct. But this would be the appropriate solution for that system of equations.